I guess. So welcome to your last lab. I'm still not sure if there's going to be an extra credit lab at the end for lab 5. I'm still undecided on that. It just depends on if I can come up with something that's worthwhile and there's enough interest in you guys wanting to do one. So Proctor Lab. This lab is again about finding the theoretical maximum dry density of a soil or aggregate. And it's going to be combined with the sand cone lab and I'm going to show you guys a nuke gauge, because normally we don't do that because we're at strata and we have that equipment available. I will show you the nuke gauge. So the way that a proctor works, the equations that we're going to be using in this is primarily moisture contents, but there's also density. So your unit weight is just your mass over your volume. So we will have no volume in our Proctor molds. I keep on saying Proctor because Proctor is just the name of the test. The Proctor molds are a steel or aluminum container, but they have no mold. We're going to be using a 4-inch Proctor mold. So for a 4-inch mold, the volume is equal to 0.033 foot cubed. So that is your Proctor mold. So what we will be doing is I'm gonna follow one of the ASTM standards. But so the way that the Proctor works is we're trying to find an optimal moisture content, and what an optimal moisture content is the amount of moisture in the soil or in the aggregate in your base to where there's enough water in there to allow sliding of all your soil particles without bringing down your unit weight. The end goal is we're going to find some sort of curve like this, where the peak of that curve is going to be that's gamma D moisture. The peak of that curve is going to be your optimal moisture content at a gamma max. Okay? The way that we're going to do this is I'm going to take a soil sample. I'm going to take a soil sample and I'm going to add moisture to it, and we're going to be at a certain amount. And I'm going to go through the procedure to add up and compact it in a certain way. Now what I'm going to have is so I'll have my mass or my mold soil, and this is wet. I'll have my mold, and this is going to be the same number all the way through. That's not going to change. My volume be 0.033 all the way through, and this is for each trials. We'll have a bunch of trials, and then we're going to have our bulk density or our wet density. Okay, so the way that this is going to work is I'm going to come up with 14.3 pounds. And on the next one, I'm going to add a little bit more moisture. I'm going to try and stair step into 2% increments. Now the actual amount of water that I add is arbitrary. It doesn't really matter. I'm just going to try and make it consistent. So if I add 2% moisture, it's not that the whole thing has a 2% moisture so if I say plus 2% moisture that I'm adding, my moisture content isn't necessarily 2%. It's just 2% from where it was. So if I add 4% to the whole thing, again, it's not equal to 4%. I just added 4% from where I started. That number is arbitrary because we're going to need to do the actual unit weight calculations anyway. But so I'll add my 4% and it'll go up a little bit, hopefully. 14.6 plus 6%, 14.8. But then when I get to, let's say, plus 8%, it might drop back down to 14.5. Okay? So what happened is my moisture content was going, or my densities were going up and up and up until it didn't. It's not quite breaking over, but we are past our optimum. On this same curve, we got to this point, this point, this point, and then we're on the other side. So now we're down here. Okay? That's essentially what's going to happen. Now, some soil samples, it'll bleed, or that you won't see the spray here. It might still go to 9. Hopefully ours won't do that. I'll try to pick out a good one, but it's a possibility. Now, the way that we're gonna correct this is, if you remember, on this curve, it's dry density, or dry unit weight, not bulk, not wet. So for each one, all we're gonna do is we're gonna take our 14.3, divide out 0.033, and that's equal to our dry, okay? So you do need this for each one of them. You know, if you're doing this live in person, we'd be doing this same day. For each one of these, I'm gonna take a moisture content out, like directly out of it, okay? So for each one, I'm gonna leave that for right now. So for each one of these, let's say our unit weight was 130. That's not what it actually is, because these numbers are all wrong. I'm not doing any math right now. Let's say it's 130.3. For each one of these, I'm gonna get a moisture content, so I'll have my pan or my tare. I'll have pan plus wet, and then my pan plus dry, and a bunch of other stuff that's the form's gonna ask you to calculate that you don't necessarily have to calculate, but eventually you'll get to your moisture content, okay? So let's say that this moisture content, this first one comes out to 3.5%. What we're gonna do, let's come over here. What I'm gonna do is I'm gonna take my wet, so my 130.3, which is on the higher side, so this is more like a 3/4 base aggregate or something. I'm gonna divide out my moisture content by 1 plus the moisture, or 1.035, just for an example on that one. 130.3 divided by 1.035. So my dry density is a 125.9. And that's my dry. Now, going back to that curve, what we're actually doing is our dry or moisture. So this first point here and here is going to be 3.5% at 125.9. And we're going to have to do that for each one of these trials. Now, when I said that sometimes you don't see it, sometimes it'll keep on going up. Just because it keeps on going up, when you actually divide this out, it will go back down. You just don't see it the first time around doing the procedure, because it is just a different type of soil that's going to leak, which is unfortunate. But I'm going to try and choose one where we will see this drop. It'll go to 14.6 or 14.6 or something. So what I'm going to try and do is get at least 2 points on either side of the curve, so that way I know I have a good curve. That is essentially it for the Proctor. Now the sand cone that's going to go with this is the field version. So what I'm getting is a theoretical maximum dry density, okay? So that's the densest it could possibly go. There's a couple different versions of doing it, which will give you different results. It's basically an old method and a new method. All the engineers out there ever like to use what's called the modify, because you get a higher value. It's more realistic to modern day technology. You'll see that on most commercial jobs, most private jobs, because the engineer will request it. For any state work that you guys will do, it'll most likely, and for ISPWC, for ACHD, it's all the modified Proctor, which is the old one, which is typically lesser values. But the sand cone's a way of figuring out what the density is in the field. Now, I don't necessarily want to be out filming on job sites, so I won't be doing this lab the way it's supposed to be done. We don't do it the way it's supposed to be done in lab anyway, so I'm not too worried about it. So sand cone. Sand cone, we're going to use the form out of the laboratory manual, because that one is set up to do in that way. It makes you do the calibration for everything. We already have all of our equipment calibrated, but that's going to be the easiest way to do it. Want to pause it? Okay, so for the sand cone, the first thing that you got to do is calibrate the sand. We got to come up with a unit weight for the sand. Again, that unit weight is just equal to your mass over volume. So what I'm going to do is I'm going to put the sand in the sand cone. I'm going to let it run out into a Proctor mold. I will get the weight of the Proctor mold beforehand, the weight of the Proctor mold with this sand in it. That'll give, if you subtract the two of them, that'll give you your mass divided by the volume, which for the Proctor mold again on the 4 inch is 0.0333. And that'll give you the dry unit weight of the sand because the sand is already dry. Next thing that we're going to need to do is calibrate the cone itself. The cone, like it sounds like, has a cone on the base and a big jug on top. So what I'm going to do is I'm going to set it up on a flat piece of ground. I'm going to let the sand run out into the cone, and that's going to give me a couple different weights. So it's my before weight of running into the cone, my after weight of running into the cone, and with that we can calculate out exactly how much extra sand is going to be on top of the hole. Now the last piece that we're going to do is going to be the actual field test. So again, I'm going to fill the sand cone back up. I'm going to go out into the field, into the backstretch a lot, and I'm going to dig a small hole. This hole, because the sand's going to come in, right? So I have my sand cone on top. It's going to be my big jug, little neck, and then cone. It's going to be on a big plate. Now underneath this plate, I got to dig a hole. Now the problem is going to be is if the hole comes out too far for this whole little section in here where it's concave out, the sand's not going to fill that. So I need to be careful, and I need to try and dig my hole basically as straight as I can. I'm going to have sand come all the way down, fill up the whole hole. I'm going to save all this material that I took out, and what I'm going to do is figure out how much sand exactly filled the hole. That'll give me my volume after I do a couple calculations to figure out exactly how big this hole was. I'm going to take this, the material that I dug when I created that hole, I'm going to dry it. So I'm going to get a moisture content on it, and based off of how much material I took out of the hole, take that same mass divided by the volume I calculated from the sand calculation, and that's going to be the sand cone. The nice thing is the Nuke gauge basically does all that for you without doing any of this extra stuff. The Nuke gauge is what you'll see on almost every job site where you gotta do some sort of compaction testing. And it'll give you my moisture content, it'll give you my density, my wet and my dry. And it basically just eliminates the whole need for the sand cone. That being said, it is a newer piece of equipment, and what my boss says is a tool. It's not always exactly right, so because of that, on jobs like the Boise Airport that we're doing right now, we have a sand cone correction factor, because sand cone is a mechanical method that's tried and true. Nuke gauge is slightly newer as of the 80s, but slightly, because they can have more variance in them. We get that sand cone correction factor. So FAA specs, you still have to have that sand cone. But that should be it, so we can go do the lab.